In this video, we're going to discuss the concepts of an equilibrium reaction. So let's take a look at this for a minute. Dinitrogen and 3H2s can combine to make two ammonias. Now this reaction can happen. This is the Haber-Bosch reaction. It's why we have modern fertilizer in agriculture. Without the ammonia we produce from this reaction, we wouldn't be able to feed humanity. So we absolutely can turn nitrogen and hydrogen into ammonia. However, if you had a tank of ammonia and you let it get hot for a while, and then you cooled it down, you looked at it again later, what you'd find is you'd have a mix of all three gases. Our nitrogen or hydrogen can indeed make ammonia, but ammonia can react with itself to break apart and make nitrogen and hydrogen. Effectively, you just have two reactions. Hey, two ammonia can react to become N2 and 3H2. The reverse of the original reaction is also a possible reaction. Instead of writing it twice, we tend to use a two-direction arrow. These can come in a variety of forms. They might be a single arrow with two direction heads, a half one, two separate ones. The idea is that we're showing the reaction goes both directions. When both reactions are reasonably possible, there's no reason to pile up on one side or the other. Some reactions are very much one-sided. If we think about methane burning with 2-dioxygen and going to CO2 and 2 waters, this is extremely one-sided. Putting carbon dioxide and water together doesn't really go back to make methane. On a more technical level, an incredibly tiny amount of it can, but it's so rare compared to the methane and oxygen breaking down that we really think of it as just one-sided. Some reactions are so extremely on one side we don't bother thinking about their equilibrium, but there's plenty of reactions where the equilibrium has to be taken into account. In the methane example, we can presume that 100% of our material becomes CO2 and water. But in the ammonia example, maybe only 80% succeeds at becoming ammonia. Maybe only 20% does, and ammonia is really good at going back to starting material. Let's think about equilibriums a little bit more. Let's imagine we have a simple reaction. X can just turn into Y. If I start a container that is nothing but X, well, give it a little time and some of it will become Y. Give it a little bit more time, another one will become Y. Give a little bit more time, another will become Y, but maybe one of the Y's goes back and becomes X. Originally, there wasn't any Y. We couldn't go backwards. But over a little time, we built up some of the second chemical, and now there was enough that occasionally some of it goes back. Well, for a while, maybe we get 2 X's becoming Y for every 1 Y that goes backwards. And so now we're up to 3 total Y's, and another one becomes a Y, and another one becomes a Y, and one of them goes back. Now we're at 4 total Y's. Our amounts are changing. I have lots of Y's, but I actually have less X as a result now. The less X we get, the less it can go forward. There's just less of them to react. So now maybe we're down to only one of them converting every time, but I have so much Y that one of them always goes back. Well, I still have 4Y and the same amount of X. Do this again. Another one could convert, and another one could go back. Well, I still have 4Y and same amount of X. At some point, we run into the problem that our amounts are no longer changing. We started with a whole lot of X and it decreased. We started with no Y and it increased. If we look at this for plots, we can have, say, moles over time. Our Y starts way down low and will pick up and then levels off at some point. Our X started high, but it dropped down and leveled off at some point. What those amounts are, whether X was really low and Y was really high, whether they were even with each other, whether Y barely got going and was pretty low, Those depend on a lot of factors with how easy a reaction is to occur, whether one gives off heat or requires heat, and things like that. But just the idea that over time one of them is going to decrease and the other is going to increase, but eventually they will stop changing. You'll reach some amounts where they no longer alter. This is called equilibrium. So at some point, and forever on from there, we reach equilibrium. Equilibrium is the point where your concentrations will no longer alter. Your reactions are still occurring, but for every one of them that changes in one direction, one of them changes back the other direction. So the amounts no longer change. This is called a dynamic equilibrium. Things are still jumping back and forth from the two sides, x's to y's and y's to x's, but they do it at exactly the same speed, the same rate, the same number per second. Well, if I give you $5 and you give me $5, we have the same amount of money. There's no change. This is the idea of equilibrium. Many reactions develop into an equilibrium. There are various things that can change it. Temperatures tend to change the equilibrium. If you slightly modify what the reactants are, so similar things may have a slightly different equilibrium position compared to some other very similar material, say a silver chloride versus a gold chloride. They both are in the same column, they both have a chloride, but whatever they're reacting with, the energetics are just a little different. There's ways we can cheat equilibrium. In fact, we do that for the Haber-Bosch reaction. Once you reach equilibrium, your amounts should no longer alter. So let's say I had a whole lot of stuff. We'll say 100 of this, 300 of that, and none of my ammonia. We gave it some time, and eventually we ended up having something like 80 nitrogen, 240 H2s, and 40 ammonias. Just some of the molecules converted. How we got these numbers, not terribly important, but hey, 20 of these, 3 times of that, I made twice as many of that. And then over time, this stays the same. It doesn't alter again. We've reached equilibrium. It took a little bit to get to these numbers, but once we were there, it doesn't alter anymore. You could leave this container there for years and it will be the same amounts. Even though some of the molecules are jumping back and forth, the totals don't change. Well, let's do a trick. Let's remove this. We take it away and turn this into nothing. Remember that I have a dynamic equilibrium. I'm still doing the forward reaction, but my reverse reaction just suddenly went away. I have no product. I can't go backwards. So as time goes on, I'm moving things to products, but they're not coming back to reactants. The amounts will change. Because I siphoned off the product, now we'll go down to something like 61, 183, and maybe like 39 of this will eventually build up. Why did I get product back? Well, I was making it. My reactants were still reacting to make products, and over time I got a little bit of product, and so the reverse built up until it matched the forward. Eventually I re-equilibrate. I reach equilibrium again. And now if we gave it more time, we'd see the same amounts. But I could just keep doing this. I could keep siphoning away that product, setting it back to 0, and exploiting the fact that, well, the forward reaction is still happening to convert more and more of my material. This is actually how we make ammonia. Ammonia isn't particularly good at being made in the Haber-Bosch reaction. We need it for fertilizer to feed all of humanity, but it doesn't work very well. Truth is, the reaction tends to dominate over here on the nitrogen and hydrogen at the temperatures we have to do this at. So if only a small fraction of my chemicals actually became ammonia and then I had to purify it and collect it, it'd be a quite wasteful process. We cheat. We can remove the ammonia. Basically, you have a big cylinder over here that has H2 and N2, and it reacts, and so the gases flowing in are H2 and N2, but what's flowing out is N2 H2, and ammonia. Well, we pump that over to another tank. And this tank is cold. What'll happen is my N2 and my H2 will stay gases, but my ammonia will liquefy. The boiling point for ammonia is much higher than for N2 and H2, so I can get it cold enough to liquefy the ammonia and leave my gases still gases. I can pump those gases back in and have them react again. Effectively, as the new H2 and N2 enter, there's no ammonia, so all it can do is produce some, get stolen, pump the starting materials back in to react again. In this way, we can pull the ammonia out. We can siphon off product each time, and we don't waste any material. We just collect the liquid ammonia, we drain it through a spigot into another container, and so we can exploit equilibrium reactions. These are considerations that have to be done when reactions are not super favorable, when they don't go predominantly to one side. Just an introduction to the concept, but the reality is every reaction is an equilibrium reaction. It just might be that it's 99.99999% on one side, so we can ignore the tiny bits on the other side because that's below our error. However, in reactions where you're somewhat close to each other in amounts, where you actually have like whole number amounts of percentages of reactants and products both present, this is a consideration that we have to start taking. You'll see more of this in Chem 162, but this is the idea of an equilibrium reaction. These are extremely common in biological systems. They're how homeostasis and self-regulation tends to work. They're how we pour sugar into our blood when we need it when we start running. This is how we remove sugar from our blood after we just eat a Snickers or a Kit Kat. Using equilibrium reactions allows things to kind of balance and maintain themselves. Pull something away, it immediately gets replaced as the other things keep reacting. Use up blood sugar and the process in your body that is storing it and freeing it up. Well, there's not blood sugar in your blood, so it can't store it, so it just keeps freeing it up. We replace the blood sugar that our muscles use by freeing it up from our storage systems. So our storage for sugar is constantly taking out and replacing sugar into our bloodstream. It's an equilibrium reaction. CO2 and dioxygen in our lungs exchanging with that in our bloodstream, it's an equilibrium reaction. So equilibrium reactions show up all over in the world and in biology. They're not rare cases. They're actually, in lots of ways, more common than one-sided reactions, but they're a little bit harder to calculate, so we don't tend to focus on them until a little bit later.